It can only get better from here.
I don't know.
Look, it can get a lot worse.
Okay. Let's go back up. So, hey guys, how you doing? All right, so guys, so far this past week or so, we've been discussing the process to take a differential equation and turn it into an equation. Now, a differential equation, like these you might see here, although these are pretty basic, represent slopes. And when I solve a differential equation through the processes we've been using, we get the equations of the actual graph. A differential equation is actually a family of opportunities, a family of options that depend on the point that I give you. And if you recall, when I solved a differential equation, I got a general solution, had a C in it. And until I give you that point, you really don't know exactly what that graph looks like. So, and if you're looking at these right now and you're thinking, well, why don't you just solve it and then you'll have a better idea about the graph? Well, that's interesting you say that. We are doing basically, I taught you differential equations in a day. You can take differential equations over a semester in college, okay? And they have that course. If you're an engineer, you'll take it. You'll spend a whole semester on it. So we don't know how to solve every differential equation. We just know how to solve differential equations at the calculus 1 level, okay? There's so much more out there. So a lot of the differential equations I will start you with in this particular part, you won't be able to solve them. Like you might be able to. I could totally do this one. I could totally do this one. But very many of them, you will not have the skills to be able to solve. Well, in that case, that would be trouble trying to solve it and graph the solution. So what we're going to do with differential equations is we're going to graph a slope field. And a slope field, just to kind of come down real quickly, give you an idea about what they might look like. A slope field might look like something like this. Where I come in there, I know, right now it looks like I would have calculated a million of them. Ours are going to be, we're not going to have that much going on. But what we do is we would go and take the point, say 1, 1, and we plug it into the differential equation. And the differential equation will spit out a slope. So we will know the slope should that curve go through the point 1, 1. You with me? So I will take that little slope and I will sketch whatever that slope would be. If the slope is 1, then I think to myself, what would rise 1, run 1 look like? And I sketch that right there. But I only just do a little segment of it. I don't go all the way, okay? Because the slope might be different at 1, 2. Like over here, the slope at 3, 1 almost looks like 0. So I must have plugged 3, 1 in there and got something that looked like a 0. So I sketch a little 0 slope. Sometimes I plug something in there and I get an undefined slope. If it's an undefined slope, the old school calculus people used to put vertical lines in there, but now they just leave it blank because technically the curve could not exist there if it was undefined. If it was a function, but sometimes it actually can exist there, like on a sideways parabola. We'll talk more about that later. A lot of times we'll just put an open circle there to represent there is no slope there, right? But it'll give me an opportunity to understand the curve. But what we're going to be doing is graphing these slope fields. Now, what I want you to be able to see here is, and these aren't that awful right here.
They are.
No. Some of these slope fields, let me find one that's real nasty. Okay. Some of these slope fields, like this one, depending, like, remember how we said a differential equation. This is representing the differential equation. And we said if I give you a certain point, the point that I give you could change what the graph looks like. Well, what happens now is I will ask you to sketch something like, sketch me the graph through the point negative 1, 1. And we'll do more of this later. Well, the point negative 1, 1 is right there. Well, this particular point right here is going to be influenced by the slopes there. Now, these slopes are all 0 right there. These slopes look negative through here. These slopes look positive through here. But what's happening here is this graph would have to actually, as it's moving along, is going to have to make sense of these slopes. So like this particular, if it went through that point, I would say, well, as I start moving left and right, it's got to mirror these points. And like right here, it's getting a little flatter. It's eventually, as I keep moving, this is 0. So it looks like it might just follow that out. This one right here, it's starting to bend a little bit. It's 0 there. Maybe it's just going to follow that out. Are you kind of seeing what I'm saying? But notice that that point gave me a completely different graph than maybe if I gave you that point. This point looks like it's flat right there. But then as it goes left, looks like it's more flat. And then as it gets this way, it looks like it really flattens out right there. But this one, as it goes to the right, looks like it's just getting steeper and steeper and steeper. Completely different look to the graph. Are y'all seeing this? Now, sometimes the graphs will look the same. Like sometimes if I plot a point here or here or here, it might just be like a sine curve that's just shifted up or shifted down. But sometimes it looks completely different. I mean, that looks like an exponential growth function. This looks like a negative logistic curve. I mean, this look right here looks like a negative exponential growth function. So sometimes the graph can completely change. All right? So that's kind of the idea of what we're doing. What you're going to be asked to do is and we're going to do that today, is sketch the slope field. And then maybe I give you a slope field and say, sketch the curve as accurately as possible that goes through that point. And I would give you a point, kind of like when you were solving a differential equation, I would give you a point. Except you would be finding the equation. Here you would be sketching the equation. Are y'all seeing this? And then other things you will do, like you'll have multiple choice questions where I'll give you a slope field and I'll say, hey, what equation do you think would go with that? Or maybe I'll say, what differential equation will go with that? So those are all things that AP Calculus would ask of you, okay? So we're gonna slowly attack this one little day at a time, and we're gonna do this over at least today and Tuesday when we get back. And then once we kind of get a handle on the slope fields, we'll just keep moving from there. So let's just go back to the slope field now that I've given you a little vision. And by the way, here's kind of a picture of an AP question. So they're not going to ask you to do a zillion points. Like this one, it was 1, 2, 3, 4, 5, 6, 7, 8 based on that differential equation. So it's not going to be like the ones we're doing today where we're graphing a zillion of them. And I'm even going to cut down on that number. It's going to be very few that you would be asked to graph. And this is not something they ask every time. But when they do, it usually is a pretty basic little question. You just have to be careful. And it's very tedious to keep plugging in the X and the Y and being careful. But it's not difficult. So check it out. We're going back up to where we were. And let's check out some of these. Okay, so let's just start out very basically with number 1. And again, we're just going to go from -2 to 2, -2 to 2. So I'm just going to pick a point. I'm going to plug it in there, find the slope, and then I'm going to do the best job I can sketching that slope. Okay? So let's start with the point. How about -2, +2? Now you might, if you're careless, and you might know if you're careless, make a chart and say x, y, and then dy dx. So if I am plugging in the point 2, -2, if I plug a 2, -2 in there, what do I end up getting? Notice the -2, there's not even a place to plug it in. So what do you end up getting? 3. So the slope is 3. So how do I sketch a slope of 3? Now, AP probably doesn't give you a whole lot where you get slopes of 3 and 4, because how are you going to really notice between the slope of 3 and 4? There's hardly any change in it. Yes? Oh, gosh. So, actually, at 2, -2, our slope is going to be 3. That's not 2, -2. At 2, -2, sorry, our slope is going to be 3. Are you with me? Okay. So, this is how I would sketch 3. I would think, well, if I was trying to sketch a line through that, I would go to the point and rise 3, run 1. And I'm going to be visualizing this line through here. You tracking with me? But I'm not going to draw a giant line because that slope very likely is going to change at 2, -1. So I'm just going to visualize that, but only put that. And then I'm going to go to the point 2, -1, which is this. And what happens when I plug a 2, -1 in there? Again, I get 3. Well, I'm going to plug a 3 there, but I'm going to think 1, 2, 3 over 1. Again, gives me this. Now, what happens when I plug in the point 2, 0? Again, get 3. And what have you just noticed? You've noticed a trend on this particular one that y had no business in this problem, did it? So for every x value of 2, for every 1, what do I get for my slope?
3.
Well, if that's the case, then just come up here and save yourself the time and just keep putting slopes of 3 all the way up and down there. Now let's come in there and go to 1, 2. Now at the slope, at the point 1, 2, which is right here, what do I get? Slopes of 2. So what would that have looked like? Well, I can either go up 2 over 1, or I can go down 2 left 1. Either way, I get a slope that kind of looks like this. But what am I going to put in there? Just a little mini version of that. What do you think 1, 1's going to give me? Again 2. And why do I know that? Because the y value bears no impact on this, does it? So no matter what happens, for every value of x, what does my slope end up being? 2. So I'm going to put slopes of 2, try to make them identical. And again, visualize, if it's 2, it's got to be pointing at down 2, left 2, or up 2 over 2. So every one is going to look like that. Now, what happens when x is 0? And I know this is tedious, but you're going to get better at these. It's 0, 2, what happens? Slope is 1. So at that point, rise 1, run 1. That's pretty easy to see. 1, 1. And all of these are 1 for the same reason the other ones were 2 and 3. Right? What happens at negative 1, 2? I get zeros. So at negative 1, for every value of x, since there is no y in this equation, I get 0 every time. Well, I put a 0 slope in there. And again, the y's don't impact it. For every x, I get that. And what happens again if x is negative 2? I get a negative 1. So I'm going to have a negative slope in the negative 1 slope. But you see how I'm lining these up each time? I'm kind of visualizing what that slope would be, and I'm keeping that slope. And I got to be fairly accurate, which is why AP normally gives you stuff like where you get slopes of zeros or positive negative 1, positive negative a half, positive negative 2, but rarely do they get it to 3 and 4 and 6, because think about it, the slope right there, there's a slope of 4, there's a slope of 3, 4, 5, 6, hardly anything's moving. It's not like they're going to pull out their measuring stick and actually check your slopes on every one. They're just, as long as you're close and have the idea, you're okay. Now I'm going to do one more just to really help you see it. What happens at negative 3 on x? It doesn't matter the y. You get negative 2. So right here you can see that slope of negative 2. When you look at this slope field, what do you see it creating? Parabolas. Now, if you're looking at that right now and going, how do you know that? Because look, if I pick any point on here, doesn't matter. I'm going to pick the point negative 1, negative 1. If I pick that point, start right there, what does it look like is happening right here? 0 slope, right? But then as I head to the right, what does it look like? What's happening? It's starting to go up, right? So it's flat right here, but the second I move in there, now I got to be kind of looking like this, a slope of 1. And then by the time I got up here, I got to look like a slope of 2. And then I got to look like a slope of 3. And I'm letting it guide me. This way, it looks like by the time I get over here, it looks like the slope's going to be a negative 1. And then a negative 2, etc. And you can see that parabola show up. And because we actually can take the differential equation here, look what happens if you integrate both sides. You get y equals x squared over 2 plus x plus c. And you can see that it's a parabola. But a lot of the time, you won't be able to see that because you won't be able to actually do the differential equation. You can't do the differential equation to this. There's no way for you, with what you know, to be able to separate these two variables and get the y's on one side and the x's on the other, because they're joined together through addition. Are y'all seeing that? Okay. So that's the whole idea. I didn't give you any points on these, so you don't have to worry about plugging stuff in. But here's the thing I want you to, you're going to be given some multiple choice questions. Like, you're only going to have to sketch a slope field. Everybody with me? Maybe one time on your test. Maybe twice, and definitely not more than once on an AP test. But what you will have to be able to do is you will have to be able to look at a slope field and pick the correct differential equation. Well, if you ever look at a differential equation slope field like this, and you're having to choose between a bunch of differential equations, if you notice that the slopes right here never change on a vertical perspective. Now they do change as you go horizontally, right? -2, -1, 0, 1, 2, 3. These are changing. But here, nothing ever changes vertically. What that means is that the y never affected the graph, did it? Well, that means if it's multiple choice, go look for equations, differential equations that don't have any y's in them. So let's just say that that was an option, that was an option, that was an option, and that was an option. I could immediately go, well, I know it's not this one because y affects the slopes here. And I know it's not this one because y affects the slopes here. And then all I would be down to is looking at these two. So that's one, and that's the same thing horizontally. If I see that the horizontal slopes never change, then that means y equals 2 was always the same. It didn't matter what the x's were, right? So if you see that it never changes horizontally, that means it never has an x in it. That would be an example like this one, right here. But if they're both changing, like as you look left to right, if you see those changing, and you look top to bottom, and you see those changing, then it's got x and y involved. Y'all seeing this? Okay, let's try another one. Hello? Is who? Oh, no, he's not in here anymore. Yeah. And no worries. No. At least one of those a day. Who said, I have no idea. They still think like driver's ed's up here. So. Okay, so let's jump down to number 3. We're not going to do all these because it just gets so mind-numbing, it's awful.
Number 3 is.
Okay, so number 3, there's a lot more going on, right? There's not a nice little pattern. So literally, again, if I made you go from -4 to 4, that's 9 numbers. This is 7 numbers. You'd have to do 63 individual slopes. I'm not going to do that. Okay? Now, there's one thing I would love for you to notice. Everybody with me on this? Come on, big guy. All right, so there is one thing I want you to really notice, and it's nice and you can do it quickly, is the slope ever 0 on this one?
Yes.
It is. When?
0, 0, -1, 1, -2, 2.
Y'all seeing that? So this is going to be 0 whenever x and y are either both 0 or what? Opposites. So that's something that's really nice. You can knock out a whole bunch of stuff a lot of times like that. So I know I'm going to get a 0 anytime those are opposites. So like -1, 1, -2, 2, 1, -1, 2, -1, etc., etc. But not 1, 1 or 2, 2. That's going to give me just bigger slopes. Y'all with me? So little things like that are worth looking at. Okay? And then at this point, I'm just going to have to suck it up. So I'm just going to say, all right, x, y, dy, dx. Let's make a chart. And you don't have to make the chart, but it's great if you make a mistake and I can go back and look and see it's careless or whatever. So I'm going to start with -2, 1. So what does -2, 1 give me? -1, so I'm going to eyeball that and draw a slope of -1 in there. And remember, visualize it. It should be going up left to that point. If it's not pointing at that point or at that point where I'm touching, then you have it off. All right, how about -2, 0? -2, so at -2, 0, I should have a slope of -2. It should be pointing right there, right? So make your slope a little steeper than it was on the point above it. What about -2, -1? -3? Well, again, it should be pointing at that. A little bit steeper than before. And then finally at -2, -2, -4, it's going to be a little steeper than that one. But at that point, it's so hard to tell the difference. Whatever, you know. Again, even if you drew the same one, I probably wouldn't. How could I count up? It's just too hard. Whatever. And AP tends to avoid that. All right. What about -1, 2? +1. So at -1, 2, I'm at +1. What about -1, 0? -1. What about -1, -1? -2. And -1, -2, -3. Have you noticed anything yet?
You just do diagonal.
The diagonals. These kind of things are worth noticing. It might make your life a little easier, but they don't always occur. I mean, sometimes it's a complete whack job what's going on, depending on what you get. Okay? But I have noticed now, look, diagonals are always the same. So I'm going to go ahead and just say, okay. And so I didn't need to go that low. This is 1, 1, 1. And again, if you're not sure, just keep plugging in there. What about 0, 2? It's 2. It's a little steeper. A little steeper. A little steeper. And then 1, 2 is 3. A lot steeper. And then finally 2, 2 is 4. And it's going to be a little. Y'all seen it? Now, if I give you the point -1, 0, hypothetically, now this is not part of this problem, but if I were to give you -1, 0, what do you think this curve does? What is it? Say it out loud. Nobody? If I gave you that point and said sketch the difference, yeah, I can't get away from this. This is constantly directing me along this line, isn't it? It's not curving, it's pointing there, so as I go up, and by the way, you'll notice I just plugged in the whole numbers. I could have plugged in fractions. I mean, I could check the point -1/2, 1/2. What's -1/2, 1/2? I'm sorry, -1/2, negative. What's -1/2, -1/2? Still -1. So if you really are unsure about, wait a minute, I don't know what happens between -1 and 0, well, plug some fractions in. The point is, I am stuck right here. This would just be a line. Now, what happens if I give you the point -1, 1? What do you think it does? It's 0 right here. But what do you think it does as it heads left?
Approaches that line.
Yeah, this thing is funneling it this way, right? So as you approach left, it looks like, well, I guess I'm just following that up. But what's it do this way? It's 0 there. It's got to be between 1 and 2 here, so maybe it's kind of, I always look at these two slopes and think, pick the middle of it. So make sure that it looks something like the middle by the time it goes in between there. And then as I'm moving this way, it's in between those two. Make sure it looks in between those two. So it kind of looks like a parabola, but it's not, because this side is moving up kind of parabolically, sort of. I don't know, it's not a parabola clearly, but it's flattening out this way. And what happens if I gave you the point -1, -1? What does it look like that graph is doing? Looks like it's got to be like this right now, but then as I move left, what's it look like it's doing? Kind of funneling it towards that line. And then as I go down, it's just getting steeper, right? Steeper, steeper, steeper. 3 different, completely different looking equations from the same differential equations, all dependent on the point that I gave you. And that's what I've been doing, right? I've been giving you a differential equation, we've been solving it, and depending on the point that I give you, you get different differential equations. Except these sometimes can really look different, because I can now give you differential equations that you can't solve. Are you seeing that? Okay. We'll do one more, number 6. Number 6, I'll make a little chart over here. Too. I'll make it right here. So, anything you notice right off the bat? They're X's and Y's, so I'm not going to have any like common value this way or common value this way, or common slope either way. Yeah, there's a bunch of them where it's undefined. I always notice that first, or I try to notice that, or notice zeros first, both of those. So anytime X is 0, it's undefined. So X is 0 on the vertical axis, so I can't have anything there. In the very first year I taught, I was having people put vertical lines in there, and then I noticed AP. Do you remember the problem I just showed you that AP was going to have you do, and you had like 8 points to plot or whatever? Did you notice that they didn't have any big dots on where it was undefined? They just avoid it. Because so many teachers teach it differently, they completely avoid it, and they go, I'm not going to even ask you to graph where it's undefined. So I'm going to remember that it's undefined. I'm not going to put verticals in there. I'm just going to leave it blank. But I'm going to remember this is undefined. And undefined can mean two things to you. It can mean either what?
Whole or asymptote.
Absolutely. It can mean there's a hole or a VA. So it might be a VA, it might be a hole. At this point in the game, I don't really know, but once I start graphing, if I see the graph start doing this, what is that telling me? Oh, it's funneling it down like a vertical asymptote. If I see the graph doing this, then my guess is it's like a sideways parabola or something, and maybe it just happened to be undefined in that one spot. But let's take a look. I'm guessing vertical asymptote. So anywhere X is 0, the slope is undefined. Doesn't matter for Y. All right, what about Y? Anytime Y is 0, the slope is 0 with the one exception of where the X is 0, right? So I could write zeros in there. I do want to do that. So zeros anywhere where the X is 0, but not here, because right here, this is undefined right through there. That whole part. So I'm just circling it. I wouldn't circle it if I were you. Just leave it blank. All right, now I just got to suck it up. Now, you do know a couple of other things. Anytime X and Y are the same, what do you get? 1? Well, if they're the same, you get 1, right? Like 1, 1, 2, 2, 3 over 3, or negative 1 over negative 1, negative 2 over negative 2. You just get 1 every time, don't you? Oh, sorry. Okay. So anytime they're the same, you get a negative 1. Anytime, if X and Y are the same, like 1, 1, I get a negative 1. 2, 2, I get a negative 1. 3, 3, I get a negative 1. So right here, 1, 1, 2, 2, 3, 3, all of these, negative 1 slopes. Except the origin, because it's undefined. And anytime they're opposites, like negative 1, 1, or 2, negative 2, or negative 3, 3, what happens there? You get positive 1 slopes, right? Because if I put a negative 1 and negative 1 and then I negate it, it's positive. So these are all positive slopes at these. So I really got a whole lot of them filled in. And oh yeah, by the way, we said we weren't going to do past the 2, negative 2. We got a lot of them, but I still have to suck it up and do some. So what about negative 2, positive 1? What does negative 2 there, positive 1 there give me? Positive 1/2. So at this point, I'm visualizing up 1 over 2. It's a little bit flatter slope. What about negative 2, negative 1? Then I get a negative 1/2 slope. So at negative 2, negative 1, I get a negative 1/2. And again, I'm visualizing what it would look like if I had a line going through there with a negative 1/2 slope, except I'm only keeping that part. What about negative 1, comma 2? If I put a negative 1 on the bottom and a 2 on the top, I get slope of 2. So I visualize a 2 there. Have you noticed any patterns? Yeah, whatever's on the top here, the negative of it's on the bottom here. Y'all seen that? Whatever's on the top here, the negative's on the bottom. If you don't notice it, just keep plugging in points. And also, whatever's on the left, the right's the negative. Left, the right's the negative. So, with some observation, I see this. Are you with me? Now here's where things can get tricky. If I gave you the point -2, 1, right there. Anybody got a guess on what this might look like? Looks kind of slope of 1/2. As I get closer, what does it look like is happening? It's getting steeper. What does it look like is going on as I go up or to the right? It's going to follow that asymptote all the way up. What do you think happens as I head this way? It's going to approach that asymptote even though I haven't done a lot of these. Now, does that look like anything you've seen before?
Yeah.
Looks like the 1/x maybe, or the 1/x squared. But the second I hit something undefined, I'm out. You got to remember that. Don't just go, oh, well, it could be over here too. Might be, but you don't know. The second you hit undefined or approach undefined, you stop. That's true even on a graph like this. Like, let me get rid of this. What if you had this? I'm going to let that represent undefined. And you had listening to over there?
Cars, the movie.
That was really fast.
I picked the wrong thing. What would you guess this is? A what? Isn't it? To me, it kind of looks like a sideways parabola. But here's the problem. If I said, hey, sketch the graph that goes through -1, 2. When you come in here, you're going, all right, I'm cruising in there, or whatever, at some point. Let's just say you got to right here, hypothetically, and you went, oh, I'm hitting that. Well, it's undefined, so you don't know whether it exists or not. The second I hit undefined, my only choice is to go, well, I don't know what happens beyond that. I do know that it keeps going that way. Second I hit undefined, I stop.
Wouldn't it also approach a zero slope on the x-axis?
Well, but remember how a undefined kind of trumps a 0? The undefined will trump anything that kind of looks like
Oh
0.
yeah, but you couldn't go past that because the slope would be 0 anyway.
Potentially, yes. Yeah. What if I had nothing there? How about that?
Well, there you go.
Then you might think undefined, perhaps, because you wouldn't have anything here. So if you had nothing there, you're thinking, oh, that's undefined. These are all kind of curving. But the point is, the second you hit undefined, you cannot make assumptions about what you think might happen. You just can't. And if you really think about the differential equation here, if I solved this differential equation, I would have this. dy over y equals dx over x. And I would have ln of y equals negative ln of x plus c. And when I eat it, I get 1 equals c. Right? I'm going to move that up there. I would get y equals swing the c. When I swing the c over, the e and the ln cancels, and I get this. What does this look like? This looks like some constant over an x. Are you with me? But because of the constant, I don't know whether it's this part and this part, or this part and this part. There's just too much unknown here, not to mention the absolute value. But it does kind of look like a 1 over x graph, doesn't it? But it's not, so my guess is it probably came from something like this, but because our knowledge is limited, I'm out. Are you with me? So, and again, you're not going to have the luxury of being able to solve these differential equations. Heck, even if you can, don't. Just remember, if I'm sketching a graph, do a point, the second I get to undefined, stop. Don't assume anything else. If I hit undefined, stop, and don't assume anything else. What do we got? 49 minutes? All right, check out this. Okay, so I have I'm going to shrink this down. Okay, it's going to be really small up here, but you have it in front of you, okay? So this is not a common looking AP question, because if it was AP, it would either do one of two things. They're not going to give you matching on the AP test. Or like this. What they would either do is give you one equation with 5 graphs and say match, or they're going to give you 5 graphs with one equation and say match. And here's the big difference. Y'all hearing this? And this is where you have to be really careful. Sometimes they'll give you the slope field, which is representing what? The differential equation. And they'll ask you to match it to the equation. So I'm actually looking for what equation could fit in that. Y'all seeing that? But then sometimes they'll give you something like this. This is on the next page, where they give you the slope fields and they say match it to the differential equation. Now the differential equation, to me, it's a little easier because all I have to do is literally check slopes. I could just take enough points and plug in enough points in there. Like if you look at number 9 on that next page, where it's sine of x, let me blow it up a little bit. If you look at number 9, I could just plug points in there. Like what happens when x is 0? What is the sign at x equals 0? 0. So the slope should be 0 on the graph. Is the slope 0 here at x equals 0? So it's not A. Is the slope 0 here? Now it very well might be. You don't actually have it drawn in there, but because it looks like -1/2 there and +1/2 there, it does look like it's probably hitting 0 in the middle. They just didn't bother to put every single one in. Right here, does it look like the slope is 0 there? To me, it kind of does. Because right here, look, it looks like this thing is kind of oscillating, doesn't it? Which definitely resembles a slope field, a sine or cosine curve. And right there at 0, it does look like it's 0. What about here? Does it look like it's 0 here? Now remember, this means every x value. Here the x values look like they might be like this. Here the x values look like this, so no. And hey, here's another thing. What did we say when there's only an x there? That there should be, along that vertical, the same stuff. Look, these are changing. Can't be that. These are all the same. Could be that. These are all the same. Could be that. These are changing. Can't be that. So sometimes you can even eliminate them. But I get down to this, and look, which one looks more like this? And by the way, I'm not looking for the sine curve, but if the derivative is the sine curve, what was the integral? When you do the differential equation, what are you going to end up with? Some kind of cosine curve? Could this be a cosine curve? Totally. Could that be? No. So you see how I'm using my intuition? But my point is, if you don't have that intuition, if it's a differential equation, all you have to do is keep plugging values in. And what other values would you plug into a sine curve? Into a sine right here. 0 is great, but what else? I'm not plugging in 1 because I don't know what sine of 1 is. Pi, and pi is about 3.14. So what's sine at pi? Pi is over here. What's sine at pi? Also 0. So go to 3.14. 1, 2, 3.14. Oh yeah, it looks like 0 there also. How about pi over 2? What's sine at pi over 2? 1. Pi over 2 is about what? What's 3-ish over 2? So at about 1.5, which is right here, I should have a slope of 1. Oh, I do. So if I give you differential equation slope fields, and I say match it to differential equations, all you have to do is just keep plugging numbers in and see if they match it. Right? Now, if I go back to what I just did before, if I give you something like this, where you have a bunch of differential equations, slope fields, whatever, and I ask you to match it to the equations, well, let's see about that. Which of these equations look like no matter what happens, I'm going to get a graph of like y equals 1.
D.
Yeah, y equals 1 is a horizontal line, right? These look horizontal. Now, by the way, this is your calculator making these. Your calculator wigs out with positive, yeah, y equals 1 should be horizontal. And when it does that, these always look like they're a little slanted. They should be zeros, but it doesn't know how to do it. It always just gives them a little bit of a hinge on them. But what about number 2, y equals 1 over x squared? What does the y equals 1 over x squared graph look like? A volcano? Where do you see where a volcano might show up? You kind of see that on A?
Wouldn't G also kind of like that?
G also would be like that, but because it's negative, I would kind of toss it. What about y equals x? Where do you see the graph y equals x? But do you see how on this one I'm not checking slopes? I'm trying to fit this line on this slope curve. But on the other one I was checking slopes to see if they match. What about y equals sine x? Now these can be confusing because look at B and look at E. Well, what's the difference between a B and an E? Or a sine and a cosine? A sine, it starts at the origin kind of heading this way, right? Not flat. And if you look at this one right here on E, it looks like it's starting right there at the origin, whereas this one over here, up there, it looks flat. Not at the origin, at x equals 0. Right here, it looks flat right there. So to me, I'm thinking this is the cosine curve. This one goes with 6, but that one goes with the sine curve. That one would go with 4. What about this F? What does it look like it's doing?
Oh, that's the X cube.
Yeah, coming up, flattening out, and then rising again. That's the x cubed, the John Travolta, right? And then what about G? G's kind of tricky. Look, yeah, look at this. This is a natural log, but how do I make it go both ways? Put an absolute value on it, and then x's can be negative, but it still gives you the same y values. And then, yeah, we've already talked about h. Hey guys, spend some time with this. This is the easiest way, the easiest problems on the test, but every year I have somebody who literally, and there's no partial credit, it's just match the slope field, and if you match it wrong, -3, -3. And I'll probably give you 5 or 6 of them, and every year I have somebody that misses like 4 or 5, and they're at 15 points on what I consider the easier problems, just because they don't practice these enough. All right. Good chat. Enjoy the long weekend.